Let's explore the second isomorphism theorem, also known as the diamond isomorphism theorem. The theorem is visualized as a diamond shape, showing the relationship between subgroups S, N, their intersection, and their product. Let's establish what we need for this theorem to work. We start with a group G and a normal subgroup N of G. We also have S, which is any subgroup of G, not necessarily normal. In notation, G is a group, N is normal in G denoted by the triangle, and S is a subgroup of G. Here's a visual representation. G is the large circle, N is normal shown in pink, and S is another subgroup in yellow. Now let's understand the key concepts involved in this theorem. The product Sn consists of all elements Sn, where S comes from S and N comes from N. This forms a subgroup of G. We denote this as the set of all products Sn with S and S and N and N. The intersection of S and N is a normal subgroup of S. S intersect N is normal in S, which is crucial for the isomorphism. The intersection shown in green is where S and N overlap, forming a subgroup that's normal in S. Here's the main statement of the second isomorphism theorem. The quotient of S by S intersect N is isomorphic to the quotient of Sn by N. This powerful result shows these two seemingly different quotient groups have identical structure. The arrow represents the isomorphism connecting these two quotient groups. Let's see how we actually construct this isomorphism. We define a map from S to the quotient group Sn over N. Call this map phi, taking elements from S to cosets in Sn over N. The map sends each element S to the coset Sn. This map respects the group operation, making it a homomorphism. Elements in S are mapped to cosets in the quotient group Sn over N. Understanding the kernel is key to proving the isomorphism. The kernel of our map phi is exactly the intersection S intersect N. Kernel of phi equals S intersect N. Using the first isomorphism theorem, we can now establish the isomorphism. S divided by the kernel is isomorphic to the image of phi. The kernel sits inside S, and factoring it out gives us the isomorphism. Let's complete the proof by showing the image is the full quotient. We need to verify that the image of phi covers all of Sn divided by N. The image equals the entire quotient Sn over N. Every coset can be written as Sn for some element S in S, so phi is surjective. Therefore, we conclude that S over S intersect N is isomorphic to Sn over N. The diamond shape gives us geometric intuition for this theorem. The diamond lattice shows Sn at the top, S and N on the sides, and their intersection at the bottom. Going from Sn down through S, or down through N, gives isomorphic structures. Let's see a concrete example of this theorem in action. Take G as the integers, N as multiples of 6, and S as even integers. G equals Z, N equals 6Z, and S equals 2Z. The intersection S intersect N equals 6Z. The product Sn equals 2Z, since both contain only even numbers. Therefore, 2Z over 6Z is isomorphic to 2Z over 6Z, which are both cyclic of order 3. Let's summarize the second isomorphism theorem. Starting with a group G, normal subgroup N, and any subgroup S, we get that S over S intersect N is isomorphic to Sn over N. This theorem reveals beautiful hidden symmetries in the structure of groups. The diamond lattice diagram captures the essence of this relationship visually.